carbon-13 NMR spectroscopy. Just as we have the number of signals corresponding to the total number of different types of protons existing in H-NMR spectroscopy, we also have the number of signals reflecting the number of different kinds of carbons in a carbon-13 NMR spectroscopy. And one major difference is the scale. When you look into the carbon-13 NMR scale, it stretches between 0 and 220 ppm, whereas in the case of HNMR, it stretches from 0 to 12 ppm. And we use the same reference compound, which is tetramethylsilane. And there is also another difference in the NMR spectrum. When you take the NMR spectrum, you can use very little amount of sample and you will still be able to get very intense peaks. But that's not going to be the case in the case of C13 NMR spectroscopy. You need lots of sample, and the reason for that is the natural abundance of C13 is going to be very less. It's only about like 1.1%, and therefore you have to use a large amount of C13. And also the gyromagnetic ratio of carbon-13 is 4 times lesser than that of the hydrogen, and therefore both of these effects add to the fact that the HNMR spectrum, the intensity of the HNMR spectrum is going to be 6,400 times greater than that of the signals received in carbon-13 NMR spectroscopy. Okay, here are the chemical shifts for the different types of carbons. And you can see that the methyl carbons are going to come somewhere between 0 and 35. And if it's going to have a triple bond, it comes somewhere between 70 and 90. And all the aromatic carbons, they come between 110 and 170. And the ketones, normally they come around like 200, somewhere between 205 and 220. And you can see like all the different carbonyl groups, they come between 165 and 200 ppm. And here is the chart that's going to give you a rough idea of like where the different types of carbons are going to get on the NMR spectrum. Here is the carbon-13 NMR spectrum of 2-butanol, and you can see there are 4 different peaks corresponding to the 4 different types of carbons present in 2-butanol. And by looking at the structure, you can see there are 2 methyl groups present on it. And this methyl group, which is far away from the electron withdrawing group, is actually going to be appearing in the far right of the spectrum. And since this methyl group is closer to the OH, it's going to come next. And the methylene carbon is going to come somewhere between 15 and 55. And we can spot that right here. This is going to be the methylene carbon. And finally, the methyne carbon is going to come between 25 and 55. And because it is attached to the oxygen, which is an electron negative atom, it comes around 70 ppm. Okay. Now, usually the carbon-13 NMR spectrum is run with the proton decoupled mode. If it is going to be run in the proton coupled mode, then you will be seeing additional splitting patterns, where you can see that this methyl group, because this methyl carbon, because it is attached to 3 hydrogens, it's going to be split as a quartet. Okay, so the number of hydrogens that is directly attached to the carbon. So 3 plus 1, that's going to be a quartet, which you can see right here. And similarly, this methyl carbon is also going to be split as quartet. And the methylene carbon, since it has 2 hydrogens in here, so it's going to be 2 plus 1. That's going to be as a triplet, which you can see that there is a triplet. And the methyne carbon is going to be split as a doublet, which is right here. And this peak is actually going to correspond to the CDCl3. If you see a peak, if you see 3 peaks like this around 77, it's going to be corresponding for the solvent CDCl3. Here are some distinct differences between HNMR and C13 NMR spectrum. First, the number of protons and the number of carbons. In both HNMR and C13 NMR spectrum, the number of signals is going to designate the number of different types of nucleus present. Say, for example, if there are 5 different types of protons, then it's going to give 5 different signals in HNMR spectrum. And the same thing is going to be true for C13 as well. So if there are 5 different carbons, it's going to produce 5 different signals. And chemical shift, the d-shielded protons are going to be existing in the downfield region, whereas the protons which are shielded are said to be in the upfield region. And the same thing is going to be true for carbon-13 as well. The deshielded carbon is going to be in the downfield region, whereas the shielded carbons are going to be in the upfield region. Next one is the integration. This is where the major difference exists between HNMR and C13. The integration, which is the peak area under the peak of the HMR signal, is going to correspond to the number of protons of that particular type. Whereas in C13, it's not going to be true. You cannot integrate like to find the total number of protons, total number of carbons present. Next one is the splitting. Normally, in H&MR spectrum, you will look into the number of neighboring protons, like in order to find the splitting of that proton. Whereas in C13, because it's going to lead to different types of different splitting patterns, we always run it in proton decoupling mode. And the reference for both of this is going to be tetramethylsilane. And the delta scale is going to run between 0 and 12 ppm on H&MR spectrum, whereas on C13, it's going to be between 0 to 220 ppm, which is actually an advantage where the different carbon signals are going to be spread on this wide range. And in order to take the H&MR sample, you need about like only 10 milligrams of the sample. But to take the C13 NMR spectrum, you need at least 30 milligrams to get a reliable NMR spectrum. And the reason for that is because the natural abundance of C13 is going to be very less, about 1.1%, and also the gyromagnetic ratio of the carbon is very less too, which in turn is going to depend on the intensity of the signals. And then finally, the H&MR spectrum is actually run on a normal spectrometer, whereas for C13, you need to have a Fourier transform spectrometer. There are also some advanced carbon-13 NMR spectroscopy, which will help us to determine the different types of carbons. Say, for example, it distinguishes between methyl, methylene, and methine carbons. And one such technique is called as the depth carbon-13 NMR spectrum, which is called as the distortionless enhancement by polarization transfer. Okay, for which you will be able to get 4 different spectrum. The first spectrum is going to give only the methyl carbons, the signals for the methyl carbons, and the second spectrum is going to give for the methylene carbons, and the third one is only for the methine carbons, and the last one, which is going to give the signals for all the different carbons, from which you will be able to identify the compound very easily. The next important technique that we have here is the two-dimensional NMR spectroscopy. There are 2 main two-dimensional NMR spectroscopy. The first one is the COSY spectrum, which comes from correlation spectroscopy. Two-dimensional NMR spectroscopy. Apart from the depth and set, we also have some sophisticated two-dimensional NMR spectroscopy, which will help us to determine interpret the NMR spectrum very clearly. And one of those techniques is going to be the COSY spectrum, which is the short form for correlation spectroscopy. In correlation spectroscopy, you will be getting 2 peaks. The one on the right is said to be the counter plot, which is going to be used in determining the interpreting the NMR spectrum, and the one on the left is going to be called as a stat plot, where you can see that there are some mountains present, and these mountains are going to exist as cross peaks on the counter plot. So as soon as you get the spectrum from the correlation spectroscopy, you are going to drop a diagonal across the spectrum, and the points which are going to be lying away from the diagonal are said to be the cross peaks. And if you're going to drop 2 lines perpendicular to each other, one parallel to the y-axis and other one parallel to the x-axis, then you will be able to reach 2 peaks, and these 2 peaks represent the 2 protons which are going to be coupling with each other. Okay, if you look into the Y cross peak, you can see that when you drop a line, drop two lines which are perpendicular to each other, and you can see that it reaches two peaks, for peak C on the horizontal line and peak E on the vertical line, right? And you can definitely tell that these are the two protons which are going to be coupled with each other. Okay, and remember, on the correlation spectroscopy, you're going to have H-NMR on both the vertical scale and as well as the horizontal scale. Okay, here is again one more example for the COSY spectrum. We have 1-nitropropane, and you can see there are two cross peaks here. The X is cross peak, where you can see that when you extrapolate this line, you can see that the A protons are actually coupled with B protons. And similarly, when you extend this line, you can see that the C protons are coupled with B protons. There is also one more type of two-dimensional NMR spectroscopy, which we call as the HETCORE. HETCORE means Heteronuclear Correlation Spectroscopy, which is going to have two different NMR spectrum. So on the y-axis, you will be having an H-NMR spectrum, and on the x-axis, you will be having a C13 NMR spectrum. And the HETCORE spectrum is going to give an indication of the coupling between protons and the carbon to which it is attached. Say, for example, if you're going to take the cross peak W, then again, you're going to drop a line, one against the y-axis, another one against the x-axis, and you can see that these protons are attached to the signal that's producing, attached to carbon that's producing the signal. Okay, so again, these 2D NMR spectrums are going to be useful in determining the coupled protons and also going to simplify the interpretation process.